Imagine we have 13 sensors attached to our body and we need to decide whether we want to walk or run for 60 seconds. Well, actually the real dataset labels it as state 0 and state 1 instead of walk and run, but I name it this way just for an illustration. Anyway, we can't tell other people our decision and they need to guess our activity based on the time series data outputted by the sensors. This is what we call as time series classification problem. Hello everyone, welcome to my channel. In this video, we will try to solve this problem using shapelet. More specifically, we will talk about shapelets and learning time series shapelets. Learning time-series shapelets, or LTS, is one of many algorithms for solving time series classification problem. Lastly, we will apply LTS to the dataset we're seeing right now. Alright, let's study together. So, what is a shapelet? A shapelet is basically a sequence, typically a short one, and this shapelet could appear anywhere in a time series. Let's say we have this shapelet of length 9. This shapelet could appear at the beginning of a time series, like this one. Or it could appear in the middle of the time series, like this one. And for this one, the same shapelet appears at the end of time series. Now, referring back to our motivating example at the beginning of the video, we want to label them as state 1 or state 0. If a time series has this shapelet, we can assign it to a label, like one of those labels. Otherwise, we will give it another label. In this example, we can group these 3 sequences into one category because they have the same shapelet. So, a shapelet is a subsequence of time series which could tell us immediately what group that is the right one for an input sequence. The subsequence length varies from the minimum length min to the maximum length max specified beforehand. Since its first introduction, there have been many variations in shapelets, but especially in the first algorithms, they almost always include these 2 stages, generating the candidates and measuring the distance between a candidate and an input sequence. The candidates are all subsequences of all time series. Their minimum length is specified beforehand, and their maximum length is theoretically the length of the time series. Let's say we have a time series of length 60 as plotted on the top plot, and we want to take one shapelet, only one kind of shapelet of length 10. All the sequences shown here are the candidates. After generating the candidates, we record the distances between a shapelet or a candidate and a time series. The definition of the distance between a shapelet and a time series is the minimum distance between a shapelet and a segment of a time series. Let me give you an example to make myself clear since this is an important concept. Okay, let's say this is our time series and this is our shapelet. When the shapelet meets the first segment of a time series, it will calculate the distance and then record it in an array. Let's say that the distance between the shapelet and this segment of a time series is 0.01, since it's very similar to, they are very similar to each other. Okay, and then after recording the distance, we will slide the shapelet so that the first element of the shapelet will meet the second element of the series. Okay, so after sliding the shapelet, this shapelet will meet a new segment bounded by the green line here now. Now that the shapelet meets a new segment, the process repeats. So the process of calculating and recording the distance repeats. Let's say that the distance between this shapelet and the second segment is 1.5. Okay, it looks quite different. Okay. After recording it, we slide the shapelet again. And so we keep sliding it, and then every time the shapelet meets a new segment, we will record the distance. Okay, so what we end up with is an array of length, the segments. So the array, the length of the array would be the total segments. After we have that full array, we would take the minimum value of this array. That is going to be the distance between this shapelet and the whole time series. Hi. So yeah, if you notice my shirt change, that's because it's another day, and I have a little situation with my recording. So anyway, we have seen the generating candidate process and measuring the distance process, and that's only for one size of shapelet, one shapelet actually, and one instance only. So if we see from the instance, we have only one instance, and one instance could generate 51 candidates. Imagine if we have 1,000 instances in our dataset, then we would have 51,000 candidates to be considered. And then if you look from the perspective of the shapelet's length, we only consider one size of shapelet of length 10. The real algorithm would also consider the shapelets with length 11, 12, up until 60 in this case. So there will be many sizes of shapelets to be considered as well. So you can only imagine how many shapelets in the shapelet space we need to consider. So naturally, these algorithms, what I mean by these algorithms is the first algorithm introduced by Ye and Go in 2009. The second algorithm is already implemented in the library skTime, and this algorithm was proposed by Hills et al. Okay, so these algorithms run very slowly. Their order of computation is O to the I squared and L cubed times L cubed, where I is the total instance in the dataset and L is the length of the time series. So naturally, researchers want to find faster algorithms, right? Some of the alternatives were already proposed and discussed in their papers. And in 2014, Graboka and others proposed a new algorithm, which is called Learning Time-series Shapelets, or LTS. And this algorithm doesn't consider all the candidates available, but they just start at some point and iteratively improve. So I guess the keyword here is the learning one, the first word in the algorithm's name. The learning here has the same sense as in machine learning. So in machine learning, when we first learned that, we learn about learning regression model and then logistic regression model. Let's say that in logistic regression model, we have a model y equals beta 0 plus beta 1 x1 plus beta 2 x2. Let's say we have two features to predict the label of y. We want to learn the optimum value for beta 0, beta 1, and beta 2, right? And we learn that through gradient descent. So imagine that we have this graph of loss plot. We have two features, so we are in 2 dimensions, and the bigger circle would indicate a bigger loss, and we want to make the loss as small as possible. So we want to go to the center of of that area. And we want to go to the better direction every time we design every step. There are so many notations involved here, like how many steps we want to take, and then how big is our step, and many others. This is the base. This is like the basic for understanding LTS, Learning Time-series Shapelets. So in logistic regression, we have equations that are differentiable with respect to each features, right? Because we want to learn these beta values. And the same logic applies to LTS here. LTS wants to find the shapelets and the weights, the beta values in this case. So they have differentiable equations with respect to the shapelets and with respect to each of the weights. Note that while in the paper it said they are using stochastic gradient descent as the optimizer for the training process, I'll be using Adam optimizer. That's what you need to look out in the coding section. And the second one is, I said earlier that this algorithm doesn't consider all the candidates. It has a scalable way to determine the total shapelets, and I'll explain that in the coding section as well. Okay, so here we are in the coding section. This is my Kaggle notebook. So I've run this before recording so that we can see the results right away. I'm running this in Kaggle because actually this is a dataset for a Kaggle competition. So unfortunately, due to the regulation, I cannot share the raw data to you guys. I will only share the code though. And furthermore, in this coding section, I will show you how I can train to learn the shapelets with only around a quarter of the data. Okay, so first of all, I'm going to implement shapelet using library tslearn. Okay, and I need to install this before doing anything because it's not pre-installed in the Kaggle. And then I also import other libraries. So this is the tslearn. And then LightGPM is for Gradient Boosting Classifier because that's gonna be the classifier, like the classification part of this problem. Now, what we have here is 4 files, the train data, the test data, and then the train labels. And this is the submission. The submission is to submit our prediction. Okay, anyway, we have around 26,000 measurements in the training data. And we have only around 600 subjects. So we can only imagine that there must be many people that who are measured more than once. Okay, we have 26,000 measurements in the training data and around 12,000 measurements in the test data. And then in the train data, I set aside 20% of it for the validation. And then 80% of it will be used for training. This is the setting, or like my setting for learning the classification model, the classifier model. However, for the shapelet, for learning the shapelet, I'm using 30% of this 80% chunk without any validation. It's not required to have a validation data. I only set 30% of the data. Oh, by the way, let me show you the code. So percentage. So I only take 30%, which is 0.3 of the whole training data that we have. I'm using only 30% because if I use all of 80% of the train data, it'll be too long. We want a faster process, and the result is still very decent anyway, so yeah, why not? Okay, so I'll go back to the top. Here's the training data, and I set the index to be like this so that it is a multi-index data frame. And then I'm going to remove the columns sequence and subject in a moment. And then you can see that we have 13 sensors here, starting from sensor 0 to sensor 12. Okay, this is the first few rows of the training data. And this is the first few rows of the test data. And there's no missing data in any sensors. Okay, we can see that there's no NA values in all variables. Perhaps because this is sort of like a toy data set. And there's no imbalance, by the way. This cell is for loading the labels. So the label is separated from the training data. The state here is our goal. We want to predict the probability, actually. So predictive probability is not a hard prediction, but only a soft prediction. We want to predict the probability that the state would be 1. Okay, so what we had earlier in pandas is a 2D data frame, right? But in TS-Learn, we need to put in the data as a 3D array. So I need to turn df. df is what I store the data frame. And so I want to turn the data frame into a 3D matrix now. Okay, this cell is for dropping or like removing the columns, subject and sequence. Now, what we have so far is a pandas data frame. Okay, pandas data frame. And then this line is to ensure that we have the same total columns, both in the training data and the test set data. And then I make 2 different functions to convert each data into a 3D matrix. Why is that? Because as I said just now, we have a pandas data frame. And then in pandas, when we want to index something, we can take the log, so log like this, and then put in the name of the index instead of the order of the index. Okay, so if the data is on the second row of the data, but the name of the index is 800, for example, then we can put 800 in this square bracket. And that's what happens in the test set data. In the test data, the first index is not 1, but instead 25968. So it's just a continuation of the training data. So that's why I need to add, because I will start from 0, and then I will need to add by the total sequence. Underscore sequence is the total sequence in the training data, which is 25968. So when I go in this for loop for the first time, I will get 0 plus 25698, which is 25698. And I will get the first data in the test data set. Okay, so yeah. And then this is where I apply those functions earlier and get my 3D matrix, so that the 3D matrix dimensions is like this. So the first dimension is the total measurements, and then the second measurement the second dimension is the length in each time series. And then the third one is the total time series. This is what TS-Learn requires us. So that's why I said it this way. And then next, we split the dataset into train and valid. This is for classification part. Okay, we will put the train dataset and the valid dataset into a classifier, the gradient boosting classifier. So that's why I still set aside 80% of the training data for training and the rest of them for valid. Okay, I set the index first and then slice the 3D matrix. And so 80% of the whole training data is this 20,700. Yeah. So we will take 30% of this, which is around 6,000 measurements for learning the shapelet. Okay, before looking at that, let me take you to see the visualization of the sensors. Okay, so this is the code for visualizing, and this is the plot. So on the left column is the sensors, or like the time series for state 0, while the right column is for state 1. Okay, and each row represents each sensor. By the way, I didn't set any seed for this visualization, so if you run this code on your machine, you might get a very different result. Okay, now let's talk about the shapelet transformation. I showed you earlier, just briefly, like showing the 30% here. Okay, so this line is actually picking the IDs, the indices that we want to take for learning the shapelet. Okay, so on second thought, I think I'll just explain it here to be more clearer. Okay, so now let's say that we have a long list like this, and then each element is the index of its own list. So it's 0 and then 1 up to 259,967. Okay, and the length of this list is 968. Okay. From this list, we split the data, right, into train ID and valid ID. So train ID and valid ID are both lists. I'm drawing the list of valid ID shorter than the list of train ID to illustrate that we have more training data than valid. And then in the training data, there are some numbers. Let's say that the last ID of train ID is 25,000. Okay. The length of train ID list is going to be the 80%, the integer of 80% of this number. Okay. So we take 80% of it and then take the integer of it. That's going to be the length of this list. From this list, we can make train X. That's what we had earlier. We have train X, and the train X is a 3D matrix. And the shape is... Okay, so the first dimension of train X is the length of the train ID list. Well, actually, train ID is an array if you see the code, but yeah, let's think for a moment that it's a list. Now, from this list, we want to take some numbers. Well, we want to take 30% of 20,000 here, which is around 6,600 something. We want to take that as a new list, and I named it as train sequence we want. So we take the train sequence we want for learning shapelets. The length of this list would be 30% of 20,000. like I said earlier, around 6,600 something. Now, suppose that the last element of this list is also 25,000. So the sequence of, the 25,000 sequence is filtered to train ID and then filtered again to train sequence we want. Okay. If we want to take the 25,000 sequence to train shapelets, the code would be train x and then square bracket 25,000. By the way, I forgot an important detail. Train x here is an ND array. So it's NumPy array. Okay. Yeah. When a matrix has only 20,000, so 20,000 rows, and we want to take the 25,000th row, it's going to give us an error, right? Because, well, we cannot do that in NumPy. In Pandas, maybe we can do that if we put loc, L-O-C, but this is a NumPy array, so we need to index it according to NumPy's rule. So yeah, this is going to give us an error. Now, what should we do then? My solution is to make a sequence, So here's our train ID. So I am going to make a train ID again, take the train ID here, and then ask each element whether that element is in the list train sequence we want. Okay, so we make another list that has the same length as train ID, but we name it not as train ID now, but instead we name it as train or no. That means we ask each element in train ID whether they are taken into train sequence we want. Let's say that we ask the first element here, and it turns out this sequence, the first sequence, is going in the train sequence we want, so we take it 1. And then the second sequence is not in train sequence we want, so we put 0. And maybe the third one is also in the train sequence we want, and then the fourth is not, and so on. So train or no would be like a true or false array. And then what we do then is indexing, And then what we do next is slicing the train x according to this true or false array. So the train x would be like this, would be sliced like this. Again, the train here, the train word here is not about train for the classification, it's not that, but train to learn shapelets. I hope that makes sense. Now I want to show you the other aspect of LTS, Learning Time-series Shapelets. Okay, this algorithm has a scalable way to determine the total shapelets and their size. So we can specify how many sizes we want and the minimum length of a shapelet, and they have their formula to calculate how many shapelets to be learned for each size. That size is like the scale actually, and it's denoted by R, both in the code and in the paper. Okay, so that was the scale of the sizes. Now, the minimum length is denoted as L in the code here. In the paper, the minimum length is denoted as L min. Okay, and it's actually the percentage of the length of the time series. or if we have unequal length of input sequence, L would be the percentage of the longest input sequence that we want to consider as the minimum length. Okay, but in this case, we have equal size, equal data points, which is 60. So the minimum length would be 15% of 60, which is 9. Okay, that's what I said. Because looking at the visualization, so I ran this code several times to look at the pattern, that I feel like the pattern only comes out if we see at least 9 data points. This is quite subjective, I know. I'm aware of it. Yeah, this is how I look at it. So our minimum length is 0.15, 0.15, so 15%. And we set the scale to be 5. So we would have 5 sizes. 1 times the minimum length, 2 times the minimum length, 3 times the minimum length, 4 times the minimum length, and 5 times the minimum length. And that is shown in the keys of this dictionary. 9 is the minimum length, as I told you earlier. So 9 is the first one, and then 9 times 2, 9 times 3, 9 times 4, and 9 times 5. Okay, this is the key of this dictionary, and it's generated by this function. And the values of this dictionary indicates the total shapelets to be learned with their key sizes. So we will have 5 shapelets of length 9, and then another 5 shapelets of length 18, and so on. They have their own formula, even though I don't know, probably I'm missing something, but I cannot find it in their paper. I cannot find the formula in the documentation either. So I only find the formula in the source of this code, of this function. So this is the formula here. The total time series in the dataset, in this case, it's 30%, 30% of 80%, 30% of the training data. Okay, and then that is multiplied by the time series size. Time series size is the length of the time series, which is 60 in this case, and then minus shape size. Shape size is like 9, 18, 12, 27 in our case, and then plus 1. This code here is showing the total segments. And then lastly, we multiply it with total classes minus 1. Since we are doing binary classification, so n classes would be 2. 2 minus 1 is 1. So basically, it's only the number of time series to train the shapelets times the segments. And then we take the logarithm, the log base 10, and then take the integer of it. So that's how they get 5, 5, 5, 5, and 4 here. Okay. This dictionary is actually one of the parameters, or the arguments in learning shapelets. The class to learn the shapelet, to implement the learning the learning time series shapelets. But I just set it to the default value. The default value would do this, by the way. So it's the same. I set the weight regularizer. That's the regularization term that we saw earlier in the paper. So it's saying like the lambda to be 0.001. And then I set the max iteration to be 2500. I don't want to be too long and overfit, so I just set it like this. Total length Total length is the scale here. It's R in this case. Where's it? R here. It's the same. So even though we don't put the shapelet dictionary into learning shapelets, but if we set the total length, TS Learn would generate the dictionary for us. And yeah. However, I feel like Atom could do well and maybe even better than SGD. It's better and faster. And then lastly, I set scale to true so that the data is normalized first before put into the learning algorithm. Okay, so here's what I do with learning shapelet here. We have 13 sensors, right? That means we have 13 variables. I'm not going to learn all these 13 variables into one learning system, but instead I will train for each sensor. In other words, I apply the trends here, the instance for learning shapelets, 13 times. And each time trends fitting and learning the shapelet for each sensor, trends will generate some values. One of them is the shapelets itself. So I'm going to put the shapelets learned in the dictionary. And then LHIST is learning history. So maybe some of you wonder how the convergence go, how fast this algorithm converge. I'm not going to show that here, but if you run this code, you can access the history here in LHIST. So the key for this dictionary would be the sensor number. So 0, 1, up until 12. And then, yeah, that's how you can get the history of each training process. I also make ND arrays for storing the transform dataset. Okay, because after we get the shapelets, we want to transform the dataset, which is calculating the distances between the learned shapelets and each time series. This is how I set the for loop. So for each sensor, I'll slice the data first. And this is just a message so that I know how many minutes have passed. Each sensor takes around 7 minutes to train with this setting. And then it fits. This is a fitting, and then this is storing the shapelets and the history. And then this is the transforming process. Okay. You see here from the minute 2 and then 6, 2 to 6, 9. So it takes around 7 minutes to train each sensor. To train the shapelets from each sensor. After the whole training process is done, we would have 2D arrays. And, by the way, I trained the shapelets with only around 6,000 data, right? That's 30% of the training data. But when I get the shapelets, I transform the whole training dataset, which is the 80% chunk earlier. Okay, that's why I have 20,000 again, 20,000 rows again in my trained shapelets, and then the valid shapelets is a 20% chunk. So it's 5,000 rows, and then the test shapelets is always the same, 12,000. Okay, and we have 312 features after training every sensor. If you divide 312 by 13, we would get 28. Wait, is that true? 24. Sorry, 24. If you sum this up, 5, 5, 5, 5, 4, we would have 24. Okay, and this is the histogram. Let's say that we didn't do the dictionary stuff earlier, and we want to know how many shapelets learned for each series, for each sizes. We would see that we have 24 shapelets. 24 shapelets for each sensor. So 24 times 13. That's why we have 312 features. Okay, now I want to plot the shapelets. What shape is captured by LTS? Okay, so this is the shapelets learned from sensor 9, and this is the first 5 shapelets. So these shapelets have length 9. Now this is the interesting part for me, because I feel like the purple and the red shapelet is quite similar, right? And then the green and the orange shapelet also look quite similar. And then the blue one is actually quite similar with the green and the orange, but it's I don't know, like the combination between the two. You might think, why we bother take similar shapelets? Like in machine learning or like in regression, if we have two similar features, that might generate bias in our prediction, or that might be multicollinearity, and we would want to remove one of them. But in this case, in LTS, a single shapelet might not be able to separate the data well, but working together, they will be able to separate the data clearly. So maybe we can think the purple and the red shapelet will work together, and then the blue, green, and orange will work as another team, maybe. And I want to show you another another shapelet from sensor 9, but it has length of 18 now. You can see that the red and the orange shapelets look really similar, and then the blue and the purple look really similar. The green is like the flip. It's like the blue and the purple, but you flip it horizontally. These plots say that if a time series has these shapelets, perhaps if a time series in the test data have a shape like in the orange and the red shapelets, then it has a high chance of being in state, I don't know, maybe state 0 or maybe state 1, but it has a high chance of being in one of the group. I'll show you another one. This is the shapelets of length 18 learned from sensor 5. You can see that the blue shapelet is the most different. It has the biggest oscillation, and then the green and the red shapelet looks quite similar. And then another group is the orange and the purple shapelets. So that's the shapelet discovery part. And then to have the prediction itself, we still need to learn or like to train a classifier model. And we're going to do that with Gradient Boosting Classifier. Okay, so this is quite similar with the first introduction of shapelet. We are using trees to try to find the best way to separate the data, to predict the labels. To train the classifier, we use LGPM classifier, and then we use 3,500 estimators. I also set the random state here. And then, oh yeah, I forgot to plot it actually, but yeah. The first iteration, AUC, oh yeah, by the way, the metric is AUC here, area under the curve. Yeah, we use this because this is the requirement for the competition. Okay, AUC is area under the curve, so the bigger the area would be the better. The minimum value is 0 and the maximum value is 1. Now look at this. Just in the first iteration, we already have 0.82. That's quite high. That's very high, actually. And then it improves really fast. It increases really fast to 0.9. It achieves 0.9 in just 78 iterations. But then starting from there, it improves quite slowly. Now we're in the middle way, around 1700 or so, and the AUC is 0.915. So even though in the iteration 78 we have 0.9, but going to the middle way, we still have 0.915. I think we ended up with 0.919. Oh, 917. This one's... these cells are for the next video. I'm thinking about to do that in the next video. So, okay. The last thing to do is to submit our prediction. So, yeah, this is loading the submission file, and then this is predicting the task sequence. Create the task shapelets, and then take the second column. And so this is the first few predictions. So here we say that the probability that the first sequence of the task data is in state 1 is 99%. Okay, so this is our CSV file. Now I'll try to submit this file, submit it to the competition. This is my very first time submitting this prediction. And I already run this notebook, but I haven't submitted for real. Okay, not bad. So when we trained the classifier, we got 0.917, right? And then in the task data, we got 0.91. This is the final. So the public score is, well, it's not the final score anyway. The private score is the final one. Yeah, maybe we overfit just a little bit. It's okay, 0.91, okay. In the previous video, I approached this problem using Rocket, and we got 0.928. It's still the best so far. Okay, so that's it for today's video. I hope you enjoy it and learn a lot. And don't forget to subscribe and hit the like button. And I'll see you next year. Bye-bye.